Welcome back, lesson 3, year 11 physics, with topic 2 forces. Please make sure you've turned to page 21 of the booklets, lesson 3 and date at the top of page 21. Quick recap on previous lessons. Lesson 1 was learning about different types of forces and in particular weight. Lesson 2 was looking at Newton's first law of motion when forces are balanced. Lesson 3 is when forces are unbalanced and looking at the motion of the object. That's highlighted in green, you can see there. And what also should be highlighted in green is this part here, Newton's second law of motion. And we'll be learning about that equation F equals ma underneath. We also need to be able to recognise that it is Newton's second law of motion, and for the exam you can state it in words or as an equation, which is F equals ma. I just copy these two underneath here because the two tie together quite usefully. They're both saying the same thing effectively. If there's no resultant force acting on an object, its velocity will not change, constant velocity. If there is a resultant force, the object will accelerate. These two here, these 2 points here, can be summarized using that equation F equals ma, meaning that if we look at the acceleration and we rearrange the equation like that, like so, if the force is constant, we can say that the acceleration is inversely proportional to the mass. So as the mass goes up, the acceleration comes down, and vice versa. If the mass is constant, we can say that acceleration is directly proportional to force. In other words, if the force increases, the acceleration increases. That's what today's lesson is really about. We'll be doing some of these worked examples in a moment, but first, let's consider these two objects. Small mass, big mass, same force. As I just mentioned, the bigger the mass, the smaller the acceleration. Therefore, this bullet has got a much larger acceleration than the car. There's an explanation for that just there. Isaac Newton's second law of motion is here. When I say here, just there, we saw it a moment ago. I'd like you now to make sure you've got a copy of that in your books. But as it says in the specification, you either need to remember that law of motion or that equation. But of course understand it. Please press pause and make sure now you've got that, including that equation, which you will write underneath in your booklets. To help explain Newton's second law of motion, this is a useful resource which is available to all of you. It's through the WJC website, and you just type into Google WJC digital resources and you can select whichever subject you want to learn more about. The particular ones that we're going to look at today, describing motion, would have been or is a very useful resource to help your understanding with the previous topic on speed and acceleration. Today though, we're going to look at forces, in particular Newton's second law of motion, and you just open that resource there. Here he is, Sir Isaac Newton, a caricature of, and it's quite useful to go first of all to this mind map. And we've already learned about what forces are. We're in the process, and we learned about balanced and unbalanced forces. Newton's laws, that's where we are at the moment, and we will be going on to terminal velocity in next lesson. Only triple science pupils need to learn about pressure and moment. So let's go back to today. Let's look at Newton's second law of motion. And the first question here is asking, can you predict what will happen when the forces are applied to the masses below? 3 identical masses, 4 different forces. Newton's second law of motion states that the acceleration is directly proportional to the force, meaning the bigger the force, the bigger the acceleration. Therefore, logic tells us that this 4 Newton force here will have the largest acceleration. And you can see that there. You can click on show answer to give a reason why as well. The bigger the force, the greater the acceleration. Let's look at another example. This time, the forces are staying the same. It's the masses that are changing. And Newton's second law of motion tells us that mass is inversely proportional to acceleration, meaning the bigger the mass, the smaller the acceleration, or the smaller the mass, the bigger the acceleration. So we'd expect this 1 kilogram mass here to have the highest acceleration. Let's see. Yeah. And an explanation. The smaller the mass, the greater the acceleration. This is the equation that you're given in your exam, and it's the Newton's second law equation that you're going to be using in a moment. This is just a useful animation that shows how to rearrange the equation. We're going to use that equation now in this worked example. It's asking us first of all calculate the acceleration, then work out the driving force acting on the car. To work out the acceleration, you use what you learnt in the previous topic. Acceleration is change in velocity over time. It's from rest, which is 0, to 32. So the change in velocity is 32 and the time taken is 4 seconds. And it takes you through step by step how to answer that, with the answer being 8 meters per second. Remember, ENO equation, number, answer, units. Part B, we use that equation and we substitute in the mass 1250 up here, and the acceleration is going to be 8. (10,000 newtons). One last worked example then before we go back to the booklet. This time you've got to calculate the resultant force acting on the aeroplane, because it's given us, it's saying the mass is 1,500. The aircraft engine produces a thrust of 18,800, but there's a drag force as well. So just pause the video and have a think about how you'd answer that before I show you. First thing you do then is draw a diagram and just show the forces acting. You should then be able to work out the resultant force is 18,000, and then you rearrange the equation. A equals F over M. Your force is going to be 18,000 and your mass is up here 1,500. And make sure to include your units.
Moving on to page 22, question 1. Total train of mass 45,000 kilograms has a drag force of 10,000 newtons, and the locomotive can produce a forward force of 40,000 newtons. What's the acceleration of the train? Always go first of all to the equation you're going to use. What do we know? Well, we know mass. We can work out force, and we're asked to calculate acceleration. So an equation with those three, F equals ma, we're asked to work out acceleration. So you just rearrange the equation with the variable you're trying to calculate on the left hand side. Force, we need to work out the resultant force. We've got 40,000 newtons in one direction, and we've got a drag force of 10,000 newtons. So all we need to do is subtract 10,000 from 40,000, and I'll do that here. I'll do it in brackets. So 40,000 take away 10,000 and divide by the mass. The mass is given at the top as 45,000. So that's 30,000 divided by 45,000. That's 2/3, isn't it? 30 divided by 45 is 2 15s and 30, 3 15s and 45, that's 2/3. 2/3 as a decimal is 0.67 to 2 decimal places. And remember, we calculate the acceleration meters per second squared. Question 2 is a past paper question. Diagram shows an aircraft and the horizontal force is acting on it as it moves along the runway. The resultant force on the aircraft is 0, Newton's first law of motion. What's meant by resultant force? You can answer that. Describe the movement of the aircraft and the resultant force is 0. Just remember, it's Newton's laws of motion, so it's either stationary or constant velocity as it moves along a runway. So that should help you choose one of those. When I say one of those two, is it constant velocity or is it stationary? The aircraft has a takeoff mass of that. Each engine produces that. Little hint here, to calculate the force being applied, you have to multiply. So this is force. You've got to multiply each engine by 4, and also kilonewtons. Every kilo is 1,000, and then you can apply the same principles to what we did there in order to calculate the resultant force. So you finish off 2B and 2C. As the aircraft moves along the runway to take off, its acceleration decreases even though the force from its engine is constant. Now I'm not going to write the answer down for you, but you need to listen now, because as the engine speeds up, what happens is there's going to be more air resistance and more drag. In other words, the force acting against the motion, which is in this direction, gets bigger. When the aircraft is accelerating, the force that way is bigger than the force that way. But just as, if you imagine you were driving onto the M4, junction 47, you come down the slip road, it goes faster, faster and faster, and eventually, even if you keep that accelerator pressed down, there's only a maximum speed you can hit. And the reason there's a maximum speed you can hit or get to is because the resistance forces will cancel out the driving force. The forces are imbalanced. The object travels at constant velocity. And remember, of course, you can't drive faster than 70 miles per hour. Okay. Show clear how you work out your answer. Just make sure as well, once you've worked out the force, that you show your equation. And now you should be able to answer 2C. So page 24, I just copied over to the right hand side here. It's asking you, task 1, label up the 3 forces with the correct term and number values. Driving force, air resistance and friction between wheels. Well, the driving force is obviously the one that's pushing the car forwards. You will label these yourself. The friction between the wheels and air resistance is the resultant force. You could, and again, you should be able to do all these now. Question 6. What does air resistance mean? It's the air particles bumping next to the object that's travelling through the air. So it's the frictional force between the air particles and the object. What is water resistance? So so you do 6. 7 you can do as well. I'll give you a verbal answer. Why is water resistance a larger drag force than air resistance? Water is denser, therefore there are more water particles per unit volume that an object would be rubbing or causing friction against as it's moving. Now, if you remember, one of the statements in the specification that you need to remember and understand is that sometimes the mass of an object can change during motion. And as a rocket launches, it's going to be burning up more fuel. The fuel is part of the mass of the rocket. Therefore, the mass here in rocket in picture 3 is less than picture 1, but the force acting up F is the same, so the force F remains the same. If the force remains the same, we can say that acceleration is inversely proportional to acceleration is inversely proportional to mass. So if the mass reduces, the acceleration increases. Therefore, if you put all that together, the acceleration is going to be largest here and smallest here. Read through the paragraph here and follow the notes underneath. A, B, C and D. The thrust from the engine stay at 25,000 newtons. So that's this force. The upward vertical force is constant at every position. So we can fill in these 2 boxes. The weight changes, of course, because as the fuel is burnt up during launch, then the mass reduces. To calculate the weight, we use the equation that we learnt in lesson 1, which is weight equals mass times gravitational field strength. We told here in part D to take gravitational field strength as 10. So, mass 2,400 kilograms times 10. The weight, therefore, is 24,000 newtons. And if this were position 1 and the weight was 24,000 newtons,
Well, I can see I've made a mistake above. That's not 2,500, that's 25,000 newtons. That's taken from here, look in the table. The resultant force there, 25 take away 24 is 1. So the resultant force is 1,000 newtons vertically upwards. And you put the answer in there. What you need to do now then is complete these cells in the table for position 2 and position 3. Read through the paragraph here and follow the notes underneath. A, B, C and D. The thrust from the engine stay at 25,000 newtons. So that's this force. The upward vertical force is constant at every position. So we can fill in these two boxes. The weight changes, of course, because as the fuel is burnt up during launch, then the mass reduces. To calculate the weight, we use the equation that we learnt in lesson 1, which is weight equals mass times gravitational field strength. We told here in part D to take gravitational field strength as 10. So, mass 2,400 kilograms times 10. The weight, therefore, is 24,000 newtons. And if this were position 1 and the weight was 24,000 newtons, well, I can see I've made a mistake above. That's not 2,500, that's 25,000 newtons. That's taken from here, look in the table. The resultant force there, 25 take away 24 is 1. So the resultant force is 1,000 newtons vertically upwards. And you put the answer in there. What you need to do now then is complete these cells in the table for position 2 and position 3.
Question 1 underneath. What happens to the acceleration of an object if you double the resultant force? A football has a mass of 1.2. A person kicks a ball with 4 newtons. Calculate the acceleration. Same person kicks the ball with twice the force. Calculate the acceleration. I'd like you to do those two, please. What's your conclusion? And your conclusion should be, if you double the force, you should find that you double the acceleration. Directly proportional. What happens to the acceleration of the object if you double the mass? So we're going to find out by actually calculating. Frisbee of mass 0.2 kilogram is thrown force of 80 newtons. You work out the acceleration there, using F over M, of course. Same mass, this time, sorry, it's not the same mass, is it? This time we got some lead tape stuck to it and thrown with the same force. Calculate its new acceleration. The Frisbee had 0.2 kilogram. What's missing here is that the lead tape stuck to it has also, yeah, it does actually state it there, has also got 0.2 kilogram of lead tape stuck. So the mass in this case is 0.4 kilograms. So it's asking, what's the acceleration? And if you double the mass. So work out the acceleration for those two, and you should find that if you double the mass, you have the acceleration. Turning over the page, onto page 28, I'd like you to read through that, and you'll be watching a video previously recorded on Newton's second law of motion, where you'll be given values for acceleration, which you need to put into your booklet, and then plot a graph of acceleration against force on the graph underneath. Okay, this is an experiment to look at the relationship between force and acceleration. What we have here is a trolley on a rail that's being pulled along, in this case by a piece of string, but that piece of string is connected to a mass or weight. So this is providing the force, and if I were to just leave that weight hang from a pulley, leave go the trolley, then the force causes the trolley to move, and in this case accelerate. If you remember Newton's second law of motion, if the forces are unbalanced, the object will accelerate. If there was no force acting, if we take the tension out of that string, if there's no force acting on an object, it either remains stationary or it would continue at a constant velocity. What we're going to do here then is change one variable. The variable we're going to change is this, the weight. And we've got a series of weights. Each one of these are a mass of 10 grams, which is 0.1 newtons. So we'll add a force of 0.1 newtons, 0.2, 0.3, 0.4, 0.5 and 0.6 newtons. And we are going to use these light gates, which are connected to this computer, to work out the acceleration of the trolley. The way that works is, if you can imagine in slow motion, as the trolley is moving through the first light gate, the light gate is able to measure the time it takes the trolley to move through, knowing that that car there is 10 centimeters. So it can work out the speed. The distance travelled is 10 centimeters, and it measures the time. It divides the distance 10 centimeters or 0.1 meters by time, works out the speed here, works out the speed here. Remember, the equation for acceleration is change in velocity or change in speed divided by time, and the computer can work out the time it takes for the trolley to go from this light gate to this light gate. Change in velocity over time. Let's set it up now so that we can make some measurements and then look to see how change in the force applied affects the acceleration. So all I'm going to do is allow the weight to provide tension to the string, and I click on start, leave go of the trolley, and that's giving us an acceleration. I know you can't see in the film, we may have a close-up later, of 0.02 meters per second squared. All we do now is exactly the same thing. The only thing we change is the weight. So we are changing the force being applied to the trolley, and we'd expect, of course, if we're increasing the force, we're going to be increasing the acceleration. So I'll hold the trolley still, I'll click on start, and that's given us a larger acceleration. We do exactly the same thing, but change one variable, the independent variable, which is the force being applied to the trolley. So we'll have a range of forces, 0.1, 0.2, 0.3, 0.4, 0.5 and 0.6. Measure the acceleration for each one. I shall make sure those results are in the next part of the video.
Now you've watched the video, the results gained from the video have been added to this table that you need to add yourselves to your booklet. They were taken from this screenshot of that very experiment, and all I've done here really is round to 2 decimal places for each one of those values that has then gone into this table. So when you analyze the results, this is what you need to do. Plot the graph on line of best fit, which must go through the origin. Calculate the gradient to work out the mass. And use the mass scale to calculate the mass of the car, card, and I'm just going to put a line through the string, the masses in the carrier, because what was being moved by the force was the car and the card, not the masses themselves. So you can put a line through that there. Also, compare the actual mass value with the gradient value from your graph. Therefore, what you need to do, and I've made a start on the graph below, is just plot in those points and draw a line of best fit. So if you can pause the video now please and do exactly that. Making sure when you draw your line of best fit that it is going through the origin, that it's not down here because all the points are above, it's not somewhere up there because all the points are below that line of best fit. So you set your ruler somewhere in between where you get a more accurate value, because we'll be using that gradient to calculate the mass. Just get a pen, or pencil I should say, obviously line of best fit, so you can rub it out, and you draw your line in. And that's pretty good, because we've got one just above, we've got 1, 2, 3, 4 pretty much on the line, and this one below. So just get rid of those 2 marks. That's the line of best fit we can work with. Now remember, when you calculate the gradient, what you need to do is, like you do in maths, is gradient is the change in the y-axis divided by the change in the x-axis. Now in our case, of course, it's our y-axis is force and the x-axis is acceleration. If we go back to our equation, F equals ma, A is F over m. So we can see change in F over, let me do that again, slight error, that's not A we're working out, it's mass. Mass is change in force over change in acceleration. That's better. So we can match that to that. In other words, the gradient gives us the mass of the car. Right, let's do that then. If we take 2 points, and I'm going to take the origin as 1 point, it just makes it easier, and I like this point. Let me use a different colour.
I'll use black here just to make it stand out from the rest. And I take this point here, and I'm going to take this point here. Now the change in force, that's on the vertical axis, is this here. So I could write that down as change in force equals, well, it's going from 0 up to this point here on the axis is 0.55 newtons. The change in the horizontal or x-axis for acceleration it'll be easier if I do it down here next to the axis itself. It's this here. Doesn't really matter where I show it, as long as you understand it's that distance going from 0 up to this point on the axis just here, which is 2.5. So our change in acceleration, 2.5 meters per second squared. Therefore, to calculate the gradient m, we need to divide the change in force, which is 0.55, divide it by the change in acceleration, which is 2.5, and that gives you a value there of 0.22 kilograms. So you can complete these parts here, and there's a few notes there underneath. When we evaluate the experiment, how we could get better, more accurate values. Or the actual mass of the car and card, would have measured that on weighing scales. It came to 230 grams, which is 0.23 kilograms. It's not exactly right due to experimental error, but that's quite accurate. So we're happy with those readings. That's the end of lesson 3. Please make sure you complete the plenary assessment study zone in Moodle, and look forward to seeing you next time. Bye.